Alright, 9.2 talks about two means independent samples. Step for hypothesis testing when applied for testing two different means. Well, the samples, so these are the requirements. The samples must be independent and randomly obtained. The values of the population standard deviation, both of those are unknown. Remember how that works? Or unequal. Populations are normally distributed, or n sub 1 is greater than or equal to 30 and n sub 2 is greater than or equal to 30. Then we assume it is normally distributed. The hypothesis testing is either a two-sided test, a left tail or a right tail. By now we are really comfortable with this. So this is two-tailed. This is left. And this is right. And if they don't specify, we use a 5%, and we're always looking for type 1 error. Choices depending on seriousness of making type 1 error. That's always the case. That's why we always look at the null hypothesis. And we're going to use a t-distribution because the population standard deviation is unknown. Just like we did before. And here's the test. Again, the null hypothesis is going to assume those are the same, so that's 0. These are the calculated. That's the first standard deviation divided by the first population, second standard deviation divided by the second population, and everything we have here we know. P-value and critical region, we're going to do both on every problem, and our conclusion is based on either rejecting or fail to reject the null hypothesis. And that's pretty much it for this. Let me go to the next page. And we start with an example. A study of zinc deficient mothers was conducted to determine whether zinc supplements during pregnancy results in babies with increased weight at birth. 294 expectant mothers were given a zinc supplement, that's N1, and the mean birth weight was, so the first batch of kids, 3,214 grams with a standard deviation of 669 grams. Now, there were 286 expectant mothers who were given placebo. The mean there was 3,088 grams, and the standard deviation was 728 grams. So instead of making our own calls and trying to say, oh, look, it's not, we're going to use statistics to figure this out. We don't look at these numbers and make any decisions because we don't know whether they're the same or they're different. Now, use alpha. So here, medicine normally we're very picky. Use alpha equal 1% significant level. And here's the question. Is there sufficient evidence to support the claim? What's the claim? That zinc supplements does result in increased birth weights. So the null hypothesis is going to say that those are the same, the population. The alternative is going to say, well, claim that what did it say? Increase. It's more than U2. Well, let's see how this works. The claim is right there. So if I reject the null hypothesis, I support the claim. If I fail to reject the null hypothesis, I cannot support the claim. So, we start off with the test statistics, and again, those are provided in that formula sheet. The test statistics, T equal, and let me fill in those, x1 minus and the way it works, we're going to take S1 squared over N1 and S2 squared over N2. Again, the assumption here is that those are the same, so this is always a 0. So this is, if I fill in the blanks, that will be 3214 and that will be 669 squared over N1294. And from the blue, I need the average, 3088, standard deviation, 728 over 286. And if I plug this in my calculator, let me get my calculator out. Okay, I squared, if I plug this in my calculator, so parentheses 3214 minus 3088 divided by, and if I take the square root and I use parentheses, 669 squared divided by 294 plus 728 squared divided by 286, 2.17. So I'm getting 2.17. Okay, that is my test statistics. Now, to use the p-value, I'm going to try to figure out what is the probability that t is greater than 2.17. And I get my calculator out, and I'll go to my distribution, and I want to figure out the t distribution, CDF, and I'm going from 2.17 to the upper 1, e to the 99. Degrees of freedom would be, oh, I didn't talk about that. Let me get that really quick. Degrees of freedom. Let me go back to the previous page. I forgot to mention that. So the degrees of freedom, will use the smaller set. So if I look at those, the smaller of the two is 286, so 285. So we always use the smaller of the two. And this probability turns out to be technology acts up a bit. Oh, come on. Here we go. So it is 1.5%, right? And remember, they gave us a 1% leeway, so this is bigger than that, which means fail to reject the null hypothesis. And if I want to use my test statistics, and that's a good idea, let's do that. Critical region, that is. The critical region method, we'll say, okay, we're looking for a t-distribution. We want this to be 0.01. Let's figure out what the cutoff point is. So I would go to my, oops, forgive me. I'll go to my distribution, and I want to use inverse tangent. And remember, this runs from the left all the way up. If the top is 1.1, then the bottom is 99%. We're going to use degrees of freedom up to 85, again the smaller one of those. And the table, 2.34. Right? 2.34. So let me get that in the notes, so in case you missed it or you want to look back at this, you know what we did. Alright, and what did we get? 2.17. Isn't 2.17 to the left of that because 0 is right there? So again, not in the rejection region. Still failed to reject null hypothesis. So again, that's because they gave us a 1%. 5% we would have rejected that. What's the conclusion? There, and remember where the conclusion was. It's right there. Test the claim that it does not, since I failed to reject this and the claim is on the alternative, I can't support it. There is not sufficient sample evidence to support the claim that, and you repeat literally what it says, a zinc supplement does result in increased birth weights. Okay, the next problem has a bit of work. A professor at a larger community college wanted to determine whether there is a difference in means of the final exam scores between students who are allowed to text in the class and those who weren't. She believed that the mean of the final exam scores for texting class would be lower than those of non-texting class. So this is a teacher that allows you to text in class and a teacher that doesn't allow you. And they're looking at final exam scores to see how that works. But her students didn't think so. So of course students are going to say, no, it's the same, it doesn't matter. But the professor wants to know, were the students correct? The professor randomly selected 30. The reason they're selected 30 from each so they could use the T or the Z distribution. And the following values are given. So one of those I'm going to do on a calculator to show how you do it. And the other I'm going to do it without the video because, you know, saving time. So let me start with the texting class. And what we're going to do, we want to input all of these values in. Let me input those first. So if you remember how that goes, we go statistics, we go edit, and we're going to clear that column. There. And we're going to input those in. So we're going to input 67.6, 70.6, 94.1, 41.2, 38.2, 88.2, 85.3, and 61.8, 64.7, 55.9, 88.2, 55.9, 82.4, 70.6. On your test, I wouldn't give you something that long. I'll pick something smaller. And now 91.2, 58.8, 97.1, 73.5, 91.2, 85.3, 94.1, 73.5, 61.8, 64.7, 82.4, and 79.4. There's one more to go. 64.7, 35.5, that's the 30th. There it is. And now if you remember how this works, we quit and we go to variables and we want to I'm sorry, we want to go to statistics and we want to calculate one variable, enter, and calculate, and there's what we need. So for the texting class, this is the data that we got. We don't need all of those, of course. They have a lot of information in there. So I'm gonna take this and I'm gonna put it right there. Now for the I need out of that, so this is how it works. The null hypothesis is stating that the means are the same. It really doesn't matter whether they do it or not. We always do that. And the professor is saying the first at texting. Yeah, they performed less than the second. That's the claim of the professor. Let's see if that works or not. Well, we have X1. The first average is 72.8. They both have 30, right? And we have the first standard deviation to be 16.92. Now, I did the calc. Oh, and N1 obviously is 30. Now, for the second, the non-texting, this part, I did that. And the average here happened to be 84.98. And the second standard deviation happened to be 11.71. And N2 is 30 as well. So the test statistics in this case, T equal, and it's going to be, we know the drill, 72.8 minus 84.98 minus 0 divided by the square root of the first standard deviation squared over 30 plus the second standard deviation squared over 30. And if I plug this in my calculator, that's negative 3.23. We know how to do that by now. Now I'm going to go for the p-value. The p-value and I'm going to use distribution TCDF from negative, that's right, to negative 3.23. I'll get that in a minute. I forgot to put the negative there. Degrees of freedom is 29. The smaller of the two, they're both the same. And there's the probability. So be careful. They didn't give us a t, did they? An alpha. So the probability that t is less than negative 3.23 turns out to be 0.15%. Less than 1%. What does that mean? Reject the null hypothesis. This is way off. And what if I want to use a test statistics? Well, we could. A test statistics, we would say, look, if you're looking at this, let's get the region out. This is 0.05, so we're going to use an inverse t-distribution. The left is 0.05, that's exactly what 1 degrees of freedom is 29. Tell us what that number is. Negative 1.70 or negative 1.699, doesn't matter. And do you see that the test statistics fall in the rejection region? Reject the null hypothesis. Well, the null hypothesis, it doesn't matter whether they text or not. Obviously, it does. And the conclusion is that there is enough sample evidence to support the claim to support, they didn't put a claim, support her belief that, and I'm trying to mimic what they said. Her belief that, and you reiterate all of that. That the mean, that's an ugly mean, that the mean of the final exam scores for the texting class would be lower than the non-texting class. And the last page of this section, we're talking about a confidence interval. Remember, if 0 appears in the confidence interval, then we assume that they are the same, otherwise we assume they are different. So the same deal as before. The error is t sub alpha over 2. There it is, that was the denominator of the test statistics. Well, x bar minus x bar plus, right? So one time you subtract, one time you minus, and we say the population is between those. You're trying to see if 0 is in there, that means H not claim is in there. And here's an example. This is how you use a confidence interval to test your claim. It says the Gallup organization wanted to investigate the time that American men and women spent hanging out with their friends. A random sample of 700 men a mean of 10 hours per week, and a standard deviation of 1.9. And on the other hand, out of 740 women, the mean time was 7.5 hours, and their standard deviation happened to be 1.6. Construct a 95% confidence interval for the difference between the corresponding population. The point estimate here is that x1 minus x2, which is 10 minus 7.5, that's 2.5 hours. That's the difference between them. We assume that's the case. We want to figure out the cutoff for a two-sided, because it's alpha over 2. So this is 0.025, 0.025, and you know how that works. It only works to the left, so I could take this left and get what that number is, and because of symmetry, use the other side, and I'm going to go for an inverse t-distribution, and 0.0.975, no, I'm going to go for 0.025. Oops. Too many zeros. 0.025. There we go. Degrees of freedom, we're going to take the smaller of those, which is 699. And that tells us it's negative 1.96. There it is. Negative 1.96 and negative 1.96 and positive 1.96. And we get the error. The error in this case is given by t sub alpha over 2, the square root of s sub 1 squared over n1 plus s sub 2 squared over n2. Well, that is 1.96. We just got it. The square root of s sub 1 was 1.9 squared, and there were 700 of them. and 1.6 squared, and there were how many were the others? 740 of them. And if I plug this in my calculator, again, we did this too many times. There it is. And construct the confidence interval. Well, it's x1 minus x2 bar plus or minus e. So that is 2.5 plus or minus 0.1819. And if I plug this in my calculator, I'll get 2.32 and 2.68. Do you notice that 0 is not in there? So, does it appear that there's a difference between men and women? There appears to be a difference, since the interval does not include 0.